So thank you, everyone, for joining us on our wild and crazy panel. We're trying something a little different here. We want to get certainly ourselves, but others as well, out of our comfort zones into thinking about hardware design in a different way. And I gave a guideline to the people who joined us that I am not interested in how you would do something. I'm interested in the question, why not? Why shouldn't we be able to do something? And then we can figure out the how afterwards. But that's the format. We have a distinguished group here joining us to help us brainstorm why not. First of all, over on my left is Nagesh Gupta, who is the founder and CEO of Lambda, and he is sponsoring this panel. Lambda is a startup which is untangling hardware and semiconductor development challenges. Nagesh has founded and sold 2 prior startups to Cadence and Xilinx, so he is truly a serial entrepreneur. And his background is in chip, software, and hardware product development. In the middle is Vidya Rajagopalan. Vidya is Senior VP of Electrical Hardware at Rivian, so the truck and car company, electrical car company, and she was previously at Tesla and Xilinx. She has extensive experience leading hardware design teams, building things from microprocessors through FPGAs to vehicle hardware. And I do want to stress that at Rivian, she is in charge of electrical hardware, the whole thing. So she's very, very capable. To my left here is Gopal Iyer. Gopal leads hardware and silicon development for Lattice Semiconductor, with an emphasis on low-power FPGAs. He previously led the development of multiple FPGA families for Altera across multiple processes, a long range of them, all the way down to 18A. So he's definitely seen a wide range of technical challenges. And then over wearing the Columbia, not sweatshirt, what do you call those things? Is Rajesh Kashyap. And Rajesh heads IP development for radio and baseband ASICs at Ericsson. He's also led silicon lifecycle management, R&D at Synopsys, and development for mobile and server class products in Samsung, Intel, and Analog Devices. And then there's one guy that we were hoping to join us who cannot make it, Amit Deer, partner in strategy and management consulting at PricewaterhouseCoopers. He did, however, leave me with a very intriguing question, so I'm going to pose that question to the panel on his behalf. But I want to start out with Vidya. So you have opinions on the need to connect design. Remember, this is wild and crazy ideas. We want to get people thinking about design in a more holistic and system level way. So you've got opinions on the need to connect design with skill sets we see coming out of college and with the native setting of modern systems design. So think C, Python, Copilot. This is an AI conference after all. Tell us more about that.
Absolutely. I think for sure, this has been actually an age-old discussion, is what people learn to code in. It used to be, I guess, C, even C was C. Now most people learn to code in Python. But in the hardware world, really, most people use Verilog. If you go stretch it, you use System Verilog. And in Europe, they used to use VHDL. and so, hardware designers is sort of a wall between the hardware designers and the software designers. And really, I personally think that if you look at all the energy and excitement going into automatic generation of code, a lot of people say, oh, we should be able to take C and just generate RTL or chips. I think we need to go, I would say, well, maybe the word now should be Python because fewer and fewer people know C and they know Python. But I would take it now and throw the challenge one step forward, is I think people will probably not need to know any of that, but we need to get tools that really generate Verilog or whatever it is, based using AI. And so that, if you look at all the excitement around how many people are vibe coding and people using AI tools to generate software code in other spaces, I think the hardware space is not going to be far. So I think people have to start getting really good at vibe coding in the hardware space. I think that's the challenge, is to really generate so that people don't really need to know detailed Verilog or any syntax, but they know how to drive AI agents to get the code they want. So good prompt engineering, I think converting natural language, build me a counter, build me something that runs on the, being able to take that kind of guidance and to generate code, then you just go fix it for whatever might be missing, or give me a little test bench that tests I have a, 4-bit multiplier, and give me a test bench for that. Give me, stimulus. I think that's what we need, is really to transcend, forget all of that. We talked a lot about it. It didn't really take off in a big way because all the EDA tools at the end were baked in and really reliant on Verilog or whatever that was. And so I think many a tool has come and gone, but I think the future should be speak in a natural language, generate the code you want. And maybe that's Verilog, but you don't care because it's way under the hood. I guess that's my big, bold call is.
So, Gopal, you actually expressed somewhat similar views for, you're coming from the FPGA space, and you want to broaden the number of people who are working with FPGAs. You want to get out there to people who are writing C code, people who are running on Raspberry Pi boards, and have them be able to build models and run models on those boards and in other contexts. Talk more about that.
Yeah, let me dwell a little bit about what Vidya was talking about and expand it. So let's take a use case, and a real world use case that's starting to take off, but I don't think we have seen the explosion of ideas just yet. So we all hear about large language models, small language models, but then you have Gemma, the Gemini, the tiny language model of equivalent of that. We have the micro llamas. So people are training their data on the larger machines, but then they're inferencing on the edge. A lot of microcontrollers, FPGAs, are already sitting on the edge of most of the complex systems. That's where your real-world sensors are. That's where the aggregation of data happens, and the data is flowing through some kind of electronic device that's sitting on the edge. So we are sort of well baked into the Internet of Things and the edge compute kind of the world. Now, if the data is locally available in context on the edge, how can we securely and with lowest latency actually infer and make decisions right then and there, rather than going it all the way to a central compute machine somewhere sitting? It doesn't take the need of going to the central compute, but if you can minimize that and have a higher latency throughput. So just imagine you have a medical probe that the doctor is working with, and on the probe itself you have enough data that it's scanning the patient or the body and giving you feedback right then and there versus going back to the central. And that's just an example on the medical field. You can see innumerable such use cases in industrial automation, in defense, aerospace. So up-leveling architectural intent and taking it all the way in through implementation. And we have gone through the phases. We've gone through Verilog, and then we went to System Verilog, we went to System C. HLS was a big thing, and all the EDA vendors are actually supporting that. But all of it is trying to teach hardware engineers higher levels of abstraction. I think the bold idea is how do you expose hardware to someone who doesn't understand hardware at all? They are pure software or natural language coders. We probably started coding in Python, Perl at some point, and then now it's Python. But now if you just have a Copilot or a GitHub, you just look for natural language question, I need a code to do such and such thing. The next thing, the code is already dropped in. So I think the same for hardware is, I think, where the explosion of ideas would happen. Yeah. And I'd just like to draw a parallel to something that has happened. Just learn from history. So if you just turn the clock back about 50 years, hip-hop culture was gaining popularities in the mid-70s in the Bronx area. That's because people had the desire to express. That got transformed in the next decade through, you went from the boom boxes to the mixtape eras. That's the Sony Walkman. You had people create their own content, disc jockeys sell it through the bodegas. Then came a decade later in the early 2000s is the internet explosion. That's where you had a global access that you have everyone who has access to internet through YouTube, SoundCloud, Spotify. And now, cut across to 2025, you have all the latest, greatest artists, the Nicki Minaj's of the world, who are at the global center stage. So from the desire to some DIY technology like tapes, to then getting into an global platform, and then there's an explosion of ideas. I think hardware has not seen that. You're still sitting in the early phases of its development on Verilog and hard-coded, and I think we need to get it all the way up to a much wider audience.
Nice analogy. So Rajesh, what do you think about this area? I mean, you're working in the wireless infrastructure world, and you have unique challenges. I constantly look at what's happening there and thinking, my God, how do they keep up with both the changes on one end and the economics on the other end? It's really, you're balancing a very delicate line. So talk to us about that.
Yeah, so I've spent about 2 decades in maybe consumer side of things in cell phone areas before, where the time scale in which a customer wants a feature in your hardware to when you can implement, it's a much shorter time. You kind of know what's coming for the next generation of iPhone 97, whatever the new number is now, right? There's not a whole lot of guesswork, I feel. I thought there was guesswork when I was doing it, but now coming into the infrastructure space, Ericsson's the forefront of building infrastructure even before the use cases are thought through. So now, how do you come up with an infrastructure? When we talk about 6G, Ericsson's in there along with a few other major players defining what 6G is. So the 6G as a concept of a project started 7 years ago inside Ericsson. So I'm looking at this going, how do you all know what you're building? We don't. So here we are. I have some of my co-workers here actually who work on the same chip that I do. We're coming into the last year before tape out. We're getting feedback now from customers saying we need these accelerations on the hardware because the software guys are going to need this for this potential app that AT&T or Verizon is going to need. We've already lost 7 years. I got the last 1 year left. And trying to take these changes, it's a no. You can't fit them in the schedule. So I think about going, I don't ever want to say no to my customer. If you want to just break through in the whole infrastructure space, you want innovation to just reach the marketplace as fast as you can. I want to be able to take a change weeks before I need to deliver a chip and incorporate it. That would involve some of the technologies Vidya's talking about, so it would involve some of the technologies Gopal talked about, but I want to kind of change the time to market scale to like really short. And then kind of going off of it, okay, well, I missed this cycle. Can I still put a derivative part out really quick because the customer wants it? So kind of break the paradigm on putting chips out. Why does it take so long? Why is it so expensive? Can we innovate our way through pace by putting chips out in the market, by enabling our customers? That's kind of how I think about it.
I couldn't agree more. That was going to be my alternate proposal is for big ideas. Today, it just takes way too long. After, let's even say you have the design done, verified, and your RTL is ready. to actually get from there to your final tape out database is just too long. And if you think about it today, there is, place and route cycles and timing ECOs. It's really, and let's just say you find a bug in one big block and you want to make major changes and resynthesize and place and route and take it all the way to tape out. That loop is so long. And if you think about it, if you've actually done that before on that same block, AI should be able to really speed the whole process up so that you get learnings from the previous cycles. So in my mind, like if you make a major change to the block, you should be able to tape out within a month. That should be a goal. And we're far from that today, right? I think.
I want weeks.
I said within a month. I'll take weeks.
So cue Nagesh.
Yeah, I think, see, we talk about going vibe coding, for example, that, Vidya talked about, higher levels of abstraction. Basically, the process of how do you get from, let's say, your prompts or your vibes to kind of, generating the code. But, there is, code is just, one part of it. You have your RTL, but then, going from that RTL to kind of, to actually creating your chip involves a lot of steps there, a lot of process. And, semiconductor design actually is one of the most complex design process that is involved, right? There's so many, in software they talk about DAGs, right? I mean, directed acyclic graphs, right? And, software, it's much easier to abstract whatever you're developing as a DAG. And that's their model of development, right? But if you look at semiconductors, right, it's hardly a DAG. It's all cyclic graphs. You're going in loops and loops and loops, right? So how do you go in a straight line? Like, let's say, you have your design, your specification, your architecture, so on and so forth, right? Today, you're basically going through squiggly, a lot of loops before you get to the tape out, right? How do you go in a straight line, right? I mean, that's the whole infrastructure part. And I think, even in this conference, right? I mean, I've been to all the different panels and, what people are talking about. There's a lot of talk about how do you go from, how do you get to your RTL from the specification or get to your UVM from the specification and so on and so forth. But there is an underlying infrastructure part that is required. There is the whole data layer. And this is going through a lot of different silos, especially in the case of semiconductors compared to any other discipline out there, right? So, and it is, it's important to make sure that, your data is consistent. Otherwise, you have started off, your intent was something, and you come out at the tape out and you realize that, hey, you know what? I mean, I've missed this feature, or, worse is you figure this out in your validation phase, which is coming in after your tape out, right? Now you're saying, okay, I've missed this feature. And so, you're going to this is depending upon the cost of your mask set and, what you have to change in the mask set, you're basically, there's that loop out there, there's the cost factor out there. And then, there was a time factor that Rajesh and Vidya talked about, right? I mean, this is complex projects taking 4 years, simple projects, 6 months to 1 year. I mean, that's actually, if you have everything so well orchestrated, you can do a 6 months to 1 year, right? But the whole idea here has to be, how do we actually, figure out, what is taking the time and how do we shorten that, right? And people talk about shifting left. But the idea here is you're getting your customer inputs in the last minute. So you actually want to shift right and make sure that your endpoint remains the same.
Good one.
Yes, just to add a bit to that, right? So I'll give credit to Synopsys and Cadence here, where the data models and stuff have come a long way, where we used to bounce in and out of tools. They've kind of worked on dragging the design from RTL through maybe sign off under the same platform. But then if you look at underneath, it's still the same atomic operation. When I came out of school, it was still the synthesis, it was still placement, it was still clocks, it was still routing, it was still sign off. It's the same atomic steps. I think one of you all said about abstraction, and we still use standard cell gates. We still use basic gates, NANDs and NORs. We got to think one level higher. We got to think about where those boundaries are from this point on. So shift in in x-axis, an X and Y axis. Another one is maybe shift up in abstraction to
Z-axis.
Z axis. That's really how we should think about this. Python, Perl, whatever. By the time we get out of this, it'll be a new language. So I'm not a software guy. So whatever the language is convenient for the kids coming out of school, that they can go from thinking to coding quick.
And I think what you guys are getting to is, we were thinking of shifting uncertainty up the food chain, but the system level requirement is actually shifting the uncertainty to the right, where if the change comes very close to tape out, or maybe it's not on the first device, but it's on the second derivative, what have we learned along the process so that we can repeat this whole thing and take in the change and get it out seamlessly? So where is that assist that can come in? I think that there is a large value in the loops that you were talking about. Those multiple iterations, there's a lot of learning that is happening. But that repeats the second time you do this whole flow.
Exactly.
And I think we need to leverage so that the second time over, you're looping far fewer times, or you have a assisting technology on the side that actually helps you ease your way through the flow to
Right.
get you to the end much quicker.
Exactly. I think that's sort of where I think we see this big convergence with AI. I mean, AI should be able to help. You put a block through once. If you made a small change, you should really be able to leverage all that work that was done before.
Yeah. So I mean, this is basically the infrastructure, right? I mean, what you need is learn from the parent and automate the derivative, right? We talk about like actually automating the parent. I think that's maybe the next step. So let's first automate the derivative, right? I mean, can we get from if you have a parent and you want to make X number of changes, can we get to the derivative in 6 weeks, right?
And the proof is in the pudding, because we are in an AI-based conference. There's a lot of investment on the training, but what you experience as a consumer is the inference, which is a much smaller model, much smaller data set, limited use case. So the repeat flow is actually the inference phase of it, where I need to do this over and over again. How quickly can I get you? Can I do a tape out from a change order to getting the tape out? Can I do it in 5 days? Like, why not? What does it take us to go there? Why are we talking about months and years?
So, Nagesh, I was thinking as you were talking about some of what you were covering, that it's sounding more and more like a kind of CI/CD kind of development flow, where you need to be able to be, and for Rajesh, where you need to be able to slot in changes anywhere in the flow and be able to cycle quickly through those changes and get a new implementation. So do we also need to think about how you can prototype what you've built? I mean, you're building hardware, so you can't just say, well, it works in simulation. You've got to, do we need to do something along those lines?
Sure. Yeah, I think, as far as the methodology itself, right? I mean, whether you want to prototype or whether you want to take it direct or whether you want to use an FPGA-based platform or one of the large systems, Palladium or whatever, right? I think that part of it is kind of, every organization has figured out what works for them, right? And a lot of the prototyping is actually required, especially when you have software and hardware, and you want to actually start developing your software a lot before your hardware is available, right? And ensure that one of the big things that happens today is there is the hardware engineer is basically looking at all the registers, and they're thinking, okay, you know what? I mean, if I change these 2 registers, and if I change the definition by just changing 1 bit here and there, right? I can solve my timing problem. And so, I'm just going to change it, right? I mean, I've told my boss that I'm going to change it and changing my hardware, my definition. And now the software guys, they've gone ahead and, they've kind of, created all the software based upon the previous version of what was written up in terms of the register definition, right? Now, granted, a lot of people actually have a lot of consistency checks that, they try to do here. But believe it or not, this is still a big problem in our industry, right? How do you keep everyone consistent? How do you make sure that, your software that is getting developed, and a simple thing like, 2 registers that were flipped or something like that can take months to debug sometimes. It's just the nature of how the debug works when you're actually using your software. and trying to bring up the system, trying to validate the system, it can take its time. So this is like the consistency problem.
I look at, I mean, once you connect the dots, right, going from specification, software needs, all the way down to what the hardware needs are. I look at the process as not as a CI/CD anymore. That feels like still a bit old school. That you're still approaching it in a monotonic way to get to where you need to get to. I'm thinking of it as you've got enough built up knowledge. You're arriving at your 99% solution right out of the bat. Maybe you're tweaking the last bit a little bit. When you ask for a change, the answer comes out without having to slowly, incrementally get there. Today, we incrementally get there, right. Even in hardware. Software is much faster loop. Hardware is still maybe a poor man's version of CI/CD. It is there. We do sprints, we do a feature bring up, we see what the verification is. It's at a different time scale. That still feels like we're not breaking the shackle if you think about it in a monotonic way versus a one-shot approach. How do you get to what you need to build with one-shot approach?
Well, I think that sort of one shot reminds me about formal verification, right? It's like, I think I've seen formal being used across projects over time, and the promise has always been there, but that's sort of one shot verification. I think we need to get more one shot, one shot synthesis place and route, correct by definition. One shot, not as much iteration as we have today, right? I think.
So I'd like to ask a little bit on the verification side, because I think both of you alluded to system definitions not being final until the last moment, well after or towards the end of the silicon, or maybe even after silicon, but during silicon or system bring up. Folding it back into silicon verification, how important is it to have all the features well defined right at the get-go and having that whole verification coverage done for that use case? And I ask this because, especially coming from the programmable silicon field, our configurations multiply into billions. You take your SerDes, you take your parallel IOs, you take all of your DSPs, your memories, you multiply all the combinations, you're talking billions of combinations. Everything cannot be verified. So there is a set user space that gets verified ahead of time. And then later on, you're figuring out that, okay, I have these use cases, can I support them? And how important is it that it has to meet your power requirement or area requirement? Or could you live with it on phase one and then you have a derivative on a phase two? From a system perspective, how do you see that?
Well, sure, I could take maybe two pieces. So I spent a very long time in the chip business, and I consciously made a move to a systems company. And one of the reasons I did that is I think you really are a better chip designer if you actually understand the system. And most chip companies struggle with the fact that the systems company they're supplying is going to just give them little information, not all of it, because they want, that's proprietary, that's their secret sauce. So they just want to give them enough to get the product they want. And as a result, you're always left guessing. I started my career building microprocessors, and we used to run benchmarks to sort of, do architecture development in the early days. Over time, you start doing applications. But even then, you're sort of guessing at what you're building based on the best known information, right? And so there are two reasons where system definitions may not be complete. There are actually multiple reasons. One is the chip, because of the long, long time it takes to build a chip. The chip is built before the systems people have started working on it. They're still working on the previous generation of hardware. They haven't had the time to even think about it. So you go talk to them, they give you a little bit of their mind share, but they go off to their day job, which is, the previous generation chip, right? And so you never get the mind share, you don't get it. Second, needs change. Something evolves, something changes, what you built. So you already assume something, and what you assume, something changed, and you miss that piece, right? So things evolve. So there's a multitude of reasons. By definition, your system design can never be perfect unless sometimes you do the whole system. Especially if you're a chip supplier, you never know the full picture for that reason. If you're a systems company building silicon in-house, you actually have the best view because you actually can go to the application developer and say, what exactly are you doing? And you can actually optimize your hardware, which is why we've seen this rise of, I think Apple started it, Google started doing it, a lot of systems companies, which used to be the old model before, way back, IBM and everything, and people went away to fabless and chip only. And now we're seeing where people have the wherewithal, Amazon, people are investing in sort of chip and application co-development for that exact reason, to close the loop. But there's always going to be this gap, and it's how well can you plug it? How well can you make it programmable so you can design for it? How can you tighten the tape-out time so you shorten the window? They're all going to be, I think, the challenges, right?
So Vidya is, I'm kind of leaning a little on Amit's comment before this conference. Is that kind of baked into the separation between semiconductor and systems companies? Or is there something that we can do to increase an awareness of systems design in the semiconductor world? I mean, it's a big ask. What do you mean by systems design? Are you talking about cars? Are you talking about HPC? What are you talking about? But somehow, are there ways that we can get a better education or a better understanding of system needs and why they appear late sometimes, and how we can kind of be flexible to those late changes?
That's a tricky question. I think if you're inherently a chip company, you're reliant on your customers to share a lot of that information. Most companies will have a so it's not the engineering team talking to the customers all the time. You do that sometimes, but there's a layer in between, a solution architect or someone who's talking to a range of customers in that space, and then they're aggregating, because you oftentimes, especially if it's an FPGA type of chip, it's not built for a purpose, but a variety of purposes. And so then you're aggregating the needs from multiple different use cases and trying to put it together. And again, that's, talk about data. That's another form of data you want to sort of get together. And it's a tricky thing because your customer's not going to tell you everything because they don't want you to share it with their competitor, right? And so I think the need to build good systems knowledge in chip companies is very important. And you build it by hiring people oftentimes that have worked in system companies that can bring that knowledge. But developing that in-house is very important.
Yeah, I think the chip industry today solves it via use cases, reference designs, you name it, and hire a few solutions architect, maybe build it out before the chip is actually sold to the systems company. So you have a longer validation period and much more thorough validation phase that happens. But I think a disruption that we would like to see here is how can we auto-generate some of these use cases? How do we define them in rules such that the use case definition, the reference design, they are all auto-generated through your validation phase, so you can accelerate all of these ahead of time versus actually serializing this or bringing it in-house like some of these larger vendors where you're building systems and they're optimizing the silicon to work with the system.
Rajesh, good point. You were describing an environment where that would be tough because things are changing on you from all directions.
That's true, but there's still the mindset of left shift again, hardware, software, co-design aspect. That's where that comes in. At least in our space, we've doubled down on generating software virtual prototypes, right? And have actual real software. So the key is to get the software guys bought in that left shift is a good thing for them, right? Otherwise, they're working on the last generation. So getting them to buy into it, getting the alignment, and then getting them to run software. Yes, you're still running speculative software. So we have a whole team that generates hardware verification test cases out of running software on virtual platform. So it's a software-driven verification model. So you don't have to verify every use case. So it kind of goes quicker because your software guys are in there. But even then, to this point, I still would get a last-minute request, right? The request is not necessarily there's a change in software model. It's about I could use a certain acceleration in hardware to do X, Y, and Z, and I wouldn't know the software guy's like, I don't know exactly in which loop I'll use it, but go ahead and do it anyways. But then verifying an accelerator, there's no software way of it. You have to verify a lot of combinations.
In hardware.
So there you get into a bit of, okay, I'm gonna have to do some blind without knowing software how I verify. So it's a blended approach. The more you can take verification higher up in abstraction, And companies like, if you're vertically integrated, this is a whole lot easier, right? The Apples and Teslas and Rivians and Ericssons of the world have, and Googles have the luxury to have the team all inside. So we had a bug 2 weeks ago. I called the software guy. I'm like, yep, I can work around it. Thank you. It's a luxury. It's a huge luxury.
I want to give some time to Nagesh here for a discussion on not solving every single one of these problems or producing new wild and crazy ideas all the way out to infinity, but to talk about one area where we can make a real difference, which is in DevOps for design.
Yeah. So, I think, system level definition is extremely important in the chip space, right? I mean, that's what, we just talked about. And one of the big problems is these definitions change. And, you think this is the definition and you have started off, doing all of your work based upon what was your initial definition. But then, you discover things. And things that you're discovering is happening later in the process, right? Now, the thing is, how do you make sure? And this is part of life, we cannot say, it's very, very, very difficult in a real situation, in a practical situation to say that, okay, give me a definition and don't change it, right? It just doesn't happen, right? So it's about change management. Change management is a critical aspect of your infrastructure, right? And today, this is one of the things that actually causes huge headaches, right? And every project that I have been in, right? A change comes in late in the project, and the intent is good. I mean, the team wants to make sure that they address the change. So they come into the room and they go through the design reviews, they go through the checklists. Everybody agrees what needs to be done. But the question is, is there a process to make sure that everything got done? Yes, there is. People try to have processes, they have checklists, again, the same thing. But, how can the infrastructure actually take care of it, right? And, this is, if you look at it today, what happens is the whole process of creating a chip, developing a chip and taking it through tape out, right? I mean, there is the whole coding, whether you're doing RTL coding, whether you're doing verification, whether you're doing physical design, there's that aspect of it, right? But then actually ensuring consistency, right? There is that other aspect. It's kind of a parallel thread, which has kind of, in a lot of ways been ignored. Or, we use methodologies like checklists, or we use methodologies like, design reviews and so on and so forth in order to do that. And the big question is, why not take advantage of some of the AI that's available, Gen AI and so on and so forth, and try to figure out how to make sure that your entire data is consistent, right? And how to make sure that when you come up with a change, and the change can be you have to plan for your change to come in as late as possible, right? That's when you're doing your job right, because otherwise you're basically saying no to your customer, right? So you want to actually enable your infrastructure such that you can accept changes as late as possible, right? And how do you do that? How do you ensure that when the changes come in, you're able to actually take care of it and automate it and make sure that these changes are reflected consistently in all parts of your design cycle?
Basically, a consistency check. Can it be built into your infrastructure? You don't have to go offline to see if you're okay or not.
Yeah.
It tells you you're okay as you're constructing.
As you're constructing, how do
That's
you make
your,
sure?
I forget the word you used about going straight and not having to constantly kind of loop back.
Correct.
Right?
Yeah.
So, yeah, straightening out the process.
And sort of identifying the handoffs and the transitions between the various phases of the design flow,
Yeah.
such that the whole approach is very seamless. It's all very well written, well documented, well trained to an AI model that just gets it done, right? It
Yeah.
just works
Yeah.
out of the box.
Yeah.
That's a really good point, because today you depend on human beings to do that, right? Somebody
Exactly.
said, did I do this project the way I did, or I found this problem last time, I added this new check, but did I remember to do it again, right? That consistency, which now largely depends on humans to do the right thing.
Yeah.
Right?
Yeah.
Yeah.
I think we were talking about this prior to the panel. we are all scared to touch legacy code.
Yeah.
And part of it is because you don't know what was done, why it was done. So you just leave it in there and you just band-aid on top of that. And I think you're saying is if you streamline the process, then there is an engine that's an infrastructure that's helping you such that you don't have to keep on piling unwanted stuff.
That's where I feel the continuous integration approach only adds versus a one-shot approach to a solution, right? If you think of the end solution one shot, you'll come up with a different answer saying, versus I'm going to create a very hierarchical way of building from step A to step Z. You'll create layers and you'll never remove anything, right? But AI should be able to say, I see the clutter, I don't need all this, I can collapse this, I want to get the final answer. And
Rajesh, can
remove
you-
interfaces, remove bugs where the interfaces are, you can get to a higher quality answer quicker if you do a one-shot approach.
Can you tell us quickly about Lambda, your company?
Yeah, so thank you, Bernard. So, see, I think, there's a lot of talk about basically streamlining parts of the design, right? And, our whole approach here is to how do you make the whole process more seamless? And how do you ensure data consistency, right? Which is the biggest problem, I believe. It has remained the same for the last 30 years that I've been in the industry, right? It's the process of doing a tape out is going through multiple checklists with multiple groups, going through multiple design reviews, right? And I say, we should still continue to do that, but how do you actually, make use of AI to streamline some of this, right? And by doing that, what do you get, right? I mean, you get your big time to market advantage. You ensure that, you have not missed that change in one location, or you ensure that you're not relying on tribal knowledge because you have your the person who did that particular check in your last tape out, right, has taken off for a week or something like that, and now you have to go through tape out, but you make sure that you can have your infrastructure that you can rely on to understand that and to take care of it automatically.
Very good. I don't know if we have 3 minutes left. Does anyone have a question? Oh, we have one question.
Hi. I was wondering if you think that the methodology of charging by licensors for EDA tools is getting in the way of improvement, because the EDA companies don't really have an incentive for things to go faster.
That's an interesting question, yeah.
Let's go get the synopsis guys and the cadence guys here. Don't start a war here, please.
I think these guys are neutral parties.
I've said this, I don't know where, maybe in an earlier conversation about, I think the whole business model needs to reinvent itself from front to back. If you want to drop the barrier for building more silicon, quicker silicon, more derivative silicon, there's R&D cost is the biggest piece. Some of the technologies that Nagesh is talking about is going to address that. But then there are other costs, NREs and license and IP and mask and wafers. Those are all they all need to kind of look at this, come together as a whole and re-look at the whole business model if you want to accelerate chip design as a way to drive innovation. Absolutely, the licenses aspect is I'm not the sales guy, so they would not hire me in sales.
I would maybe add the licenses. I mean, today you can get licensed by the hour, or you can get seats, right? You can unlimited hours. You pay for the year or something like that. It's less that. I think it goes back to there's so much development that goes in this EDA world. And unlike sort of software development, the consumer pool, the customer pool that pays for it is very small. So if you had more people building chips, then you could amortize that tool development cost over a larger set of people.
Yay,
Be
Gopal.
cheaper, right?
So not only that, but I think the software guys, if you look at all the SaaS guys who are building the software tools outside of chip design, they actually charge by use. I think thankfully semiconductor has not yet gone there, but I think from a business model perspective, that might be an interesting way to look at it, because most of the licenses and EDA tools have already gone on the cloud, so it's all by seat. But is it by use? And maybe that's probably, does it drop the barrier really? And that's something to go look at.
Well, that's definitely a good incentive to get more people designing on demo boards or hobby boards or whatever, because then They'll all be using those tools.
Any thoughts on open source tools?
Any
Open
thoughts?
source. Our clock is down to 27 seconds, so a really fast answer.
Well, I would say people use Verilator a lot in the Verilog space, so I think there's definitely room for that. It's when it becomes, I think, yes, that should be the future. It's harder when it's tied to a process node. So that's why Verilog is very obvious. It's node independent. So I would say open source tools that are not yet process specific is a great way to start with, right?
I think there's a lot of learning that can be leveraged from there, like Chips Alliance and F4PGA and all that. There's a lot of common knowledge that gets built if you have open source out there. I think how the data privacy, that's where we need to make sure that although it's open source, but you're still maintaining the privacy of the end application.
Well, I'd like to thank this group. First, Nagesh for setting this up. Rajesh, Vidya, Gopal, thank you very much for joining us. And thank you for attending.
Thank you.
guys.
Yeah,
Thanks for
thank
attending.
you.
Thank you.